Hi. Today we've got the PAT paper from 2008 going through the second lot of multiple choice questions, questions 18 through 22. So in question 18, we're told that a lecture theatre is located 3 metres east and 4 metres above a reception. And we're asked to calculate the minimum energy needs to be expended by a receptionist to travel this distance to go to the lecture theatre. Well, we're told nothing about the route that the receptionist must take, and we're told nothing about the speed that he or she will walk at. So the way to start thinking about this question would be, well, what energy can I actually calculate? The only information we really know is how far away it is. And think about, well, if it was the minimum energy needed. Let's imagine somehow she could go from the reception and just travel diagonally upwards to the room, to the lecture theatre. That would be the minimum amount of energy you have to expend. She just goes straight there on a diagonal path. Well, if she did that, what energy would she have to expend? Well, the only way she'd be losing energy is from the work she does against gravity. So what is the work she does against gravity? Well, the change in GPE will be equal to her mass times the gravitational field strength times the height she goes through. And what that's equal to, we're told she's 60 kilograms times gravitational field strength 10 times the height she goes through. That's 4 meters. So that's 2,400 joules as the minimum amount of energy. So that's B. Okay, so we're told that a phone has a 3.6 volt battery and it produces 0.7 amps for 1 hour. We're told it can be charged by a square solar panel of side length 25 centimeters, and that assuming 10% efficiency at instant solar power of 1 kilowatt per meter squared, what time is needed to charge the battery? Okay, so what do we know? Well, let's start with the first. We've been given a voltage and a current, and that they produced this for a certain period of time. Well, what do we know about voltage and current? Well, we know that power is current times voltage, and therefore energy is current times voltage times time. So how much energy does the battery produce? So the energy stored in the battery when it's fully charged will be the current it produced 0.7 times 3.6 times some time t, and we'll do it in hours because if we do it in some arbitrary hours and keep the unit constant, it's not a problem. So this means that the solar panel needs to produce this much energy. So the solar panel will produce, the area of it is 0.25 meters times 0.25 meters, which is 1 over 16 meters squared. So that's the area of panel. Okay, so how much power does it produce? Well, therefore, power is 1 kilowatt, 1 times 10 to the 3 per meter squared, times the area, which is 1 over 16 meters squared. So that gives us 1 over 16 times 10 to the 3 watts. So that's how much power we get from our solar panel. So we require the energy produced, that's power times time, so that's 1 over 16 times 10 to the 3 watts, times the time it runs for, t, in hours, to be equal to the energy that the battery requires. Well, that's 0.7 amps times 3.6 volts times the time in hours, which is 1 hour. And therefore our time is equal to 0.7 times 3.6 times 16 over 10 to the 3. And that comes out to roughly 0.4 hours. So the answer is C. So question 20 is an LDR is connected to a 12 volt source in a desert. And we're asked, when is the power dissipated the highest? Okay, well, what do we know about power? Well, power is current times voltage. And current we know is voltage over resistance. So that's equal to V squared over R. Okay. So we have different formulae for power. We have the current times voltage, and we have the voltage squared over resistance. We have the voltage. Do we have the current? Well, no. Do we have the resistance? No. But we do know that it's an LDR. And what do we know about LDRs? Well, LDRs have the following property. As the light intensity increases, the resistance, in fact, falls exponentially. So we're going to have a minimum resistance at the time of maximum light. And the type of minimum resistance, well, that be v squared over the smallest number, which will be the largest power. So our largest power dissipation will be when the resistance is the lowest. And we see from this graph that the resistance is the lowest when the light intensity is the most, and that is going to be at noon. So the answer is noon C. Okay, so in question 21, we're told that a 10-gram bullet is fired at 400 meters per second into a cubic tank of water, 2 meters on all sides, and it's brought to rest by friction. And we'll also calculate the temperature change of the water. Okay, so we know a relationship with temperature and energy. Well, Q, the energy required to raise some fluid by some temperature delta T, is equal to the mass of the fluid times the specific heat capacity times the change in temperature. So when the bullet is fired, it comes to a stop, and it's brought to a stop by a force. So that force must do work on the object. This frictional force must do work on the bullet to stop it. And as it comes to a halt, and clearly the only energy it had at the start is kinetic energy, the frictional force must do work equal to the bullet's kinetic energy. So friction does work to stop bullets. So the frictional, we'll call it WF. So the work done by friction, well, that will be equal to the kinetic energy at the start. That's half times the mass, which is 0.01 kilograms, times the velocity squared. So that's 1/2 times 1 times 10 to the minus 2 times 16 times 100 squared. That's 1/2 times 10 to the minus 2 times 16 times, well, 100 is 1 times 10 to the 2, so that square is 1 times 10 to the 4. So that comes out as 8 times 10 to the 2 joules. So that's how much work the frictional force must do. Well, this is going to produce heat. So with friction, when you rub objects together, as you know, friction produces heat. So we're going to assume that this energy, the work done by friction, goes into heating up the water. So that will be Q. So therefore, our energy, 8 times 10 to the 2, is equal to our mc delta T. Well, mass is density times volume times C delta T. So delta T is in fact equal to 8 times 10 to the 2 over density times volume times C. Well, what is that? Well, we've been told the density of water in the question is equal to 1,000 kilograms per meter cubed. So that's 1,000. The volume was 2 by 2 by 2, so that's 8. And the heat capacity we know is 4,200 joules per Kelvin per kilogram. So that's times 4,200. Well, 8's cancel, so we get 10 squared over 4,200, 4.2 times 10 to the 3 times 1 times 10 to the 3. That's 4.2 times 10 to the 6. So that comes out to give us 1 over 4.2 times 10 to the minus 4. 1 divided by 4.2 is approximately 0.25. That's approximately 0.25 times 10 to the minus 4. So the answer is 2.5 times 10 to the minus 5, which corresponds to an answer of A. So in question 22, we're told that in Einstein's equation, E equals mc squared, a student enters the mass in grams and the speed in meters per second, and we're asked what units will E have? Well, let's think about this. So normally joules would be the unit of energy in this equation, when mass is in kilograms and the speed of light is in meters per second. What we notice is, in fact, we've had it entered in grams. So that means our right-hand side has been multiplied by 10 to the minus 3. So that means our left-hand side must also be multiplied by 10 to the minus 3. And what is 10 to the minus 3 of a joule? Well, that is clearly a millijoule. So the answer is A, millijoule.